Today we have Yupeng Zhang with us, and he will talk about his work, Zero Knowledge Proof, and its applications in machine learning. Let's introduce the speaker. Oh, let's welcome the speaker, sorry.
Thank you.
Anything wrong?
Okay. Is everything good now?
Yeah, it's green
So,
now. Cool.
hello, can you hear me?
Yeah.
Yes.
Yes.
Okay, good. Okay. All right. So yeah, I was saying. So what is zero knowledge proof? A zero knowledge proof is this cryptographic protocol that can prove the validity of certain statements without revealing the sensitive information. So in a zero knowledge proof, there are two parties. There's a prover and a verifier, and the prover has a piece of secret data. And because this is a crypto seminar, I can formally say that this is usually called witness of the prover. So using zero knowledge proof, okay, this does not work now. Okay. So using zero knowledge proof, the prover can make a claim about this witness. For example, we can say that on a public computation C, executed on this witness together with some public input gives you this result together with a proof. And the verifier is able to verify the correctness of this proof using correctness of this claim using the proof and result in the public computation. And there are two major properties of a zero knowledge proof system. The first one is called soundness, meaning that if the prover is malicious, he can do whatever he wants, but the probability of making a wrong claim but still passing the verification is negligibly small. The second property is called zero knowledge. So this time, if the verifier is in turn malicious, or whoever gets access to this proof and the result, the proof leaks no information about the prover's secret witness beyond the fact that this claim is true. This computational result is this one. So that is a zero knowledge proof. So since zero knowledge proof was introduced by Goldwasser, Mikhail, and Rokov in 1985, it has seen great applications in many areas in practice. And I guess the most popular application of zero knowledge proof is in the blockchain domain. So basically, blockchain cryptocurrency is a way to build so-called decentralized digital currency by posting these transactions on this public authenticated data structure like this. And by asking everyone to kind of validate the correctness of these transactions, we can reach so-called distributed consensus and get this distributed cryptocurrency without a trusted a centralized server. And the total market cap of all cryptocurrencies right now already exceeds $1 trillion. And the underlying technique of blockchain itself is interesting and has led to many new applications such as decentralized finance, NFTs, and more recently Web3. However, in this blockchain domain, still there are some challenges, and the two of them are privacy and scalability of blockchain cryptocurrencies. So first, in these public blockchains, everyone can join and leave, so there's no mutual trust among the users. There's no privacy guarantee of the data posted on the chain. Everyone can just download a copy and access to the data posted on the chain. So that's why privacy is a big issue. Another issue is the scalability. And here I'm showing you an example of the throughput of Bitcoin. So Bitcoin can process about 5 transactions per second for all users around the world. And that's actually quite low. If you compare it to the centralized payment system like Visa cards is dealing with 65,000 transactions per second. So there's a big gap in terms of scalability. And using zero-knowledge proof, we can actually address these two issues by posting a proof about the validity of these transactions on the chain instead of these transactions themselves. So using this approach, we can achieve privacy-preserving cryptocurrencies, and we can also improve the scalability using a technique called ZK rollup. And in particular, we can batch a lot of transactions, thousands of transactions into one small succinct proof and post it on the chain instead. So because of these applications, blockchain becomes one of the most important technology in the blockchain domain. And a lot of companies are working on developing products using these protocols. And many of these companies already have billion-dollar valuations. So beyond blockchain, zero-knowledge proof also has other applications. And here I just want to highlight one from my own research. That's the application in the machine learning domain. So as everyone knows, machine learning algorithms are used everywhere nowadays. For example, it's been used in credit card risk predictions for loan approval and card approval, and used in criminal justice to kind of predict the recommitment of a crime. And it's also used in healthcare for health insurance. And in many of these applications, the machine learning model is actually an intellectual property and valuable assets of the companies and institutions. So they are not willing to share the parameters of these models to the public. So in this case, how can a regular user know whether this machine learning is fair and not biased towards certain attributes like gender and race? As a regular user, we just merely receive a final decision without any justification. So it turns out zero-knowledge proof can be potentially used to address these issues. So using zero-knowledge proof, the companies can actually generate a proof proving that these machine learning models are indeed satisfy certain notion of fairness, and later further prove that the inference is really made from the same machine learning model without revealing the parameters of the machine learning models. So in this way, we can achieve some kind of the trustworthiness of the machine learning model, and at the same time preserve the confidentiality of the models.
So here training is not involved.
No, we haven't considered training yet. So we assume that model is already trained and owned by the owner of the model.
Okay.
Yeah. So because of these cool applications, zero-knowledge proof has become a very active research area in recent years. So it was selected as 10 breakthrough technologies, and also people in our community are organizing these standardization workshops, working with people from industry and governments, trying to standardize these protocols and assumptions.
In the previous slide, can you see who's the prover and who's the verifier?
The company is a prover and the public is the verifier.
And what kind of statement?
I'm going to talk about it in the second part of the. Yeah, I'm going to talk about it.
Verify has a component of the data. I don't understand what that is.
Yeah, I'm going to give you some background on fairness and machine learning and proof in the second part of the talk. Yeah, just keep that in mind. Yeah. So and also there was a block growth of the number of papers on zero-knowledge proofs, and here I'm just taking a very small subset of papers, focusing mainly on those with implemented systems. And as you can see here, the system can be based on various different cryptographic techniques like bilinear pairing, secure computation, discrete log, and so on and so forth. And my research in this area is mainly focused on developing efficient schemes based on interactive oracle proofs and interactive proofs. And I'm going to talk about this later in this talk. So in a zero-knowledge proof system, we care about the following efficiency measures. So first, we have the proof size and the verifier time. And because of these applications, we want them to be as small as possible. So in particular, we want the proof size to be asymptotic smaller than the size of the computation and the data, and also the verifier to be even faster than computing the computation from scratch. And we call those systems as succinct. And we already have very good proof systems with succinct proof size and verifier time. In addition, we also have the prover time, which measures the overhead to generate this proof. And turns out in most of the existing zero-knowledge proof schemes, this prover time is at the bottleneck of the schemes. So in order to generate such a proof, it introduces an overhead of 5 to 6 orders of magnitude compared to merely running the computation without any security guarantee. And the main sources of this high overhead comes from these two major computations. The first one is the fast Fourier transform algorithm, and the complexity is quasi-linear, like L log n. And the second one is modular exponentiations over large finite fields, and the complexity of which is also superlinear. So other than this challenge, there's also another issue called trusted setup. So in some of the schemes, other than the prover and verifier, there's also another party called preprocessor, who has to generate a secret key and derive some public parameters in order for and send them to the prover and verifier in order to run this program. After that, a critical step is the preprocessor has to delete the secret key completely. Otherwise, the security of the scheme will be broken. So this is not desirable in practice, and is called the issue of a trusted setup. So my research in this area is trying to address these two issues. And in terms of general purpose zero-knowledge proof, I actually proposed a new framework to build zero-knowledge proof using the building blocks of interactive proofs and polynomial commitments. And in this framework, I developed an efficient zero-knowledge proof scheme with a strictly linear prover time. And I also we also removed trusted setup in this framework. So then, other than general purpose zero-knowledge proof, I've also looked into some specific applications of zero-knowledge proof. In particular, we've kind of initiated a study of zero-knowledge proof for machine learning inferences, and we have some schemes for decision tree and convolutional neural networks. And I've also looked into some applications for proving the correctness of program analysis on some secret programs. So today I'm going to mainly talk about these two papers. The first one is the general purpose zero-knowledge proof called Orion, which was published in this year's crypto. And the second one is the ZKCN paper for convolutional neural networks that was in CTS 2021. So then I'm going to start with the general purpose zero-knowledge proof. So in order to understand how can we build a kind of succinct proof system, I want to start with a particular example called polynomial evaluation. So in this example, the prover has a secret polynomial fx like this, a0 plus a1x plus and so forth, adxt, a degree d polynomial. And instead of sending it to the verifier, the prover wants to commit to this polynomial using a commitment like a hash or Merkle hash tree. And later, the verifier can make a query about a polynomial evaluation at point R. And then the prover can make a claim about this f of R together with a proof for the verifier to check the correctness. Okay? So basically, this is a special example of a zero-knowledge scheme for polynomial evaluation only, and where the secret data is the polynomial and the computation is polynomial evaluation. So in this case, so let's ignore the zero-knowledge property for time being and focus on the soundness. How can the verifier check that this polynomial evaluation is correct without seeing the entire polynomial with only a succinct proof? So that's our goal now. So the solution to this problem is called polynomial commitment. So here I'm just first going to show you a solution with a square root d size proof in the degree of the polynomial. Okay, that is sublinear, and you can also call it succinct based on different definitions. Okay. So the way we do it is first we are going to arrange the coefficients of this polynomial into a matrix of dimension square root d times square root d. Okay. And by the way, here I'm listing the standard equation of polynomial evaluation. So then it's actually not hard to show that the polynomial evaluation is equivalent to a vector matrix product followed by another inner product. So we're going to multiply this vector generated by different powers of this evaluation point R from 0 to square root d times this matrix. The result is another matrix, another vector of square root d. Then we are going to do an inner product between that vector and the other vector generated by the evaluation point. Okay, so it's actually not hard to see that you're basically multiplying each coefficient with the corresponding power of this point. So the result is a single value, which is f of R. Okay. So with this relationship, then the question becomes: so if the prover can actually prove the correctness of the first computation, the vector matrix product, and sends this vector of size squared d to the verifier, then the verifier can just compute the second step on her own. Just multiply it with the second vector and get the result of evaluation. So if we have a scheme to prove the correctness of this computation, then we will have a scheme with square root proof size, because the result of this computation is only of square d in the degree of the polynomial, right? So now that's our new problem, proving the vector matrix multiplication. So the tool we are going to use to build this scheme.
Sorry, I missed it. How does this matrix correspond to the polynomial again?
Just arrange the coefficients, I think, column-wise. So this is it's not very clear. So this is like A0 here. Oh, where's my cursor? A0, A1, A2, all the way to A squared D, and then A squared D plus 1, like that.
So is this procedure repeated many times with different R?
So for each, no, the matrix is independent of R. So
Yeah.
this matrix is committed
the
once.
procedure, not the matrix.
Yeah, so for every different evaluation, you need to generate a different proof. So yes.
So is it like the sentence verify or can verify can compute the final evaluation result?
Yes, in this example, yes. But in our paper, we have better approaches to further reduce the proof size, but I'm not going to do the details of it. Okay.
Also, I think there was a question in the chat. Can I use the same randomness for different polynomials?
There's no randomness involved. I'm just using R to represent the evaluation point. Maybe I could use a different letter. Yeah. So this is a particular evaluation point R, not any randomness involved. Okay. So the tool we're going to use to build this scheme is error correcting code. Okay. So this is a well-studied classical topic in the area of communication, information theory, network coding, so on and so forth. So an error correcting code encodes a message of size k to a code word of size n, which is larger than k. And you can think of it as a constant multiple of this message. Okay? And the most important property of an error correcting code is the distance, okay, which measures the number of locations that are different between any two code words. Okay? And good distance means that there's a large fraction, like constant fraction of locations are different between any two code words. For example, half of the locations are different. Okay? And if a code has this good distance, then you can use it to correct errors and for other applications. So that is an important feature of error correcting code. And then linear just means that the linear combination of any two code words is still a code word. And this linear code is the most commonly used error correcting code in practice. Okay? So with this error correcting code, then the solution works as follows. So first, we are going to encode each row of this coefficient matrix using this error correcting code. And the result is another matrix, encoded matrix with slightly larger dimension. Okay? So then we are going to commit to this each column of this encoded matrix. You can think of it as computing a hash for each column, or you can use a Merkle hash tree to compress commitment into a constant size. Then the prover is going to compute the result of the product between this first vector with the encoded matrix. The result is a vector of the size that is same as one row of this matrix, the encoded matrix, and then send it to the verifier. Then, because of the linear property of the error correcting code, if the verifier decodes this answer, then she can actually recover the original answer of the product between the vector and the original coefficient matrix before encoding. And the size is very big. Yeah.
How many commits do you need to make here?
If you just use Merkle hash tree, then it's just single hash.
Okay, so it's like you are committing to the whole.
Yeah, I view each column as the value in one leaf.
Okay.
Yeah.
Okay.
Yes.
So what's the difference between this and the situation when you simply think about every leaf as one particular entry in that matrix?
I think it's essentially the same, because if you view it as a subtree in that leaf, then at least in terms of complexity, that's the same.
Okay.
Yeah. So then, yeah, again, I was saying if you decode it, you can get the original answer you want. So now the final question is, how can we make sure that this vector is computed correctly by the proof? Because the verifier only sees the commitment to this matrix, It may not even be a good matrix, it may not even be an encoded matrix. So then the check is actually not very straightforward. First, the verifier is going to check that this vector is still a code word. That is true if the prover is honest, because the linear combination of any two code words still gives you a code word. Second, the verifier
knows this. What is the verifier know? I'm confused about this.
just this result. Yeah, send it to the verifier.
Only the result, but the verifier know the linear transformation.
Yes, this query is generated from, so this vector is generated from the evaluation point. So the verifier knows the evaluation point that unknown.
It doesn't know this matrix, but it knows what.
Just this result and the R here.
Actually, really why you're describing it in terms of decoding. The prover should send the
Code word.
not
The message.
point, but it should send the message and then encode it.
Yes, sure. Yeah, actually that also works. And that's how.
You don't have to check whether it's a code word, you know it's correct, right? And you never have to invoke the decoding.
Yes, actually that's right.
As you know, it's important.
And also that's how it's implemented in practice to save some bandwidth.
So
Yes,
what are you sending right now, the whole vector?
Yeah, so I'm sending this entire vector, which is a code word, and then you decode it, that's the result. And we are saying that you can also send this message first, and then you encode it to recover the.
You send this decoded message.
Yeah, so either way works. Yeah, but anyway, so then the second step is the verifier is going to check several columns randomly. Okay, so what does that mean? So the prover is going to send these random columns chosen by the verifier directly to the verifier, and the verifier checks they're consistent with the commitment in the first step. And each column is actually has a valid path in the Merkle tree or is the same as computing the hash. Then the verifier also checks.
You're committed to the encoded matrix.
Yes, encoded matrix.
Okay.
Yeah. And then the verifier is going to check that the inner product between this vector and each column equals to the corresponding location in this answer. Again, that is true if the prover is honest, just by the definition of vector matrix allocation. So that is the second check.
So I guess you are not assuming the verifier knows the commitment of the original polynomial, like it knows the commitment of this.
Yeah, commitment of the transformed the encoded matrix. Yes,
Okay.
but you can actually track the polynomial from this encoding.
So is this scheme decay?
No, I'm going to just briefly talk about how to do it
Okay.
just by masks, doing some random mask. Yeah, not no ZK yet. Okay. So then the claim is that if you do these two checks, then with high probability, this answer is correct. So why is that? Here's a very simple proof sketch by contradiction. So if this answer is not correct, then by the first check, it is still a code word of this error code, which means that the distance between this wrong answer and the correct answer, which is another code word, is actually very big. There are many locations that are different between this code word and the correct code word, the correct answer. Then by the second check, if you open one column randomly, then the probability that it is still the same as the commitment and the inner product between this vector and the open column is the same as this location is constant. So if you have half of the locations are different, then by checking one column randomly, you get a cheating probability of 1/2. Okay? Then by opening 100 columns randomly, then you can get the cheating probability of a negligible, like 1/2 to 100. So that is the intuition of the soundness of this scheme. So, but just by the distance and linear property of the error. Yes.
There's also the details. You have to be sure that the original commitment was actually a commitment.
Yes, there's another step which I didn't show it because there's the automated test. Yeah. Yeah. But actually just same test, same scheme, same arguments. Yeah. So anyway, so that actually gives us an example how to do this polynomial commitment using error code. I change it to a problem vector of matrix product, do the encoding, and then relying on this distance of the error code to check the correctness. And this approach has been used in several prior work, and they were using this classical Reed-Solomon code to encode each row. And the distance is actually very good, but the problem of Reed-Solomon code is that encoding time is quasi-linear, out of d log d using the FFT algorithm. So in order to further improve the prover time, so we have to figure out a new approach relying on another type of error code that can be encoded in linear time, but still with good distance.
I got it objectively. What?
Yeah.
That's the citation.
Sorry, what?
This is his paper. I want the link.
No, I'm saying that this is my paper I'm going to talk about today, and I mean your paper will appear on this expander code a lot of times.
Okay.
Yeah. Sorry, I already included in the related work part, and I'm going to include again the expander code and
Okay,
everything.
but the new approach is not.
Oh, okay, then I see that's the confusion. I'm just saying that in other
The new approach is work that Orion is based on.
yeah, based on a sequence of prior papers on linear time encodable code. Yeah.
I see.
Sorry, how?
So are you
sure.
saying this linear time code was used in some earlier paper?
Yes, yes.
I see.
Okay, so here's the earlier paper. Well, it's for the expander code part, but not the zero knowledge part. Sorry about the confusion. So, but and then and I was saying that in order to make it faster, we need this code that can be encoded in linear time, and this still with a good distance. So, and actually, we have such a type of code in the literature. So this code is usually called expander code, constructed using expander graphs. And the particular one I was referring to was proposed by Daniel Spielman in 1996, and later extended by Zhang Shai to finite field, and also later used in Ria's paper with his co-authors to construct this zero-knowledge schemes using the mechanism I was discussing as a polynomial movement.
The other paper isn't the first to use the linear code to construct.
No.
But
no.
these papers, are these papers used? I mean, the Spielman is just a linear code paper.
Yes.
So what are those other zero-knowledge proof papers?
No, DI 14 extends this code into the finite field. And then this GOS 2021, they changed the kind of construction code slightly, but still based on expander graph. And in this paper, they also propose a zero-knowledge proof scheme. But actually, the major contribution in our paper, you can see later that we have an efficient way to generate such an expander graph that achieves the sumness for the first time.
What do you mean by efficient? Like, you mean concrete computation?
I mean, I'm going to talk about it now. Yeah. So the expander code is actually constructed using this expander graph. And here I can, this example, this is a bipartite graph. There's a left set of nodes and right side of nodes connecting with each other only. And expander means that any subset nodes expands to many nodes on the right-hand side. For example, here you can see every 2 nodes connect to at least 5 nodes on the right-hand side. And this is a very good expansion because the degree of the node on the left, like the outgoing number of outgoing edges, is only 3. It's a constant. So at most, 2 nodes can connect to 6 nodes, but it already connects to at least 5 nodes. So the expansion is actually pretty good in this graph. And so that is an expander graph. Then if you have such a good expander, then the encoding is as follows. So we're just going to put the messages into these nodes on the left, and then we are going to sum them up using the nodes on the right-hand side through these connections. For example, here's a node with these 2 edges, then you just sum these 2 values and put it into the right nodes, and that is, you can think of it as the code word of this version of encoding. And this encoding is actually quite simple and efficient. So you can actually achieve linear time encoding using this approach. And so in the prior papers, they formally proved that you can actually have a constant relative distance, like constant fractions are different, if this expander graph is actually a very good,
The
has a very
average
good
degree
expansion.
of each node on the left
Is a
side
constant.
is
Yes, yes. And but actually, a note here is that this is only one step of encoding. The real encoding is much more complicated, which requires a recursive construction, because for some simple expansion, this one cannot have a constant relative distance. But I'm not going to talk about the details there. We're just applying this one recursively again and again to construct the real encoding of the code. So yeah, and so then here's the part about our contribution. So then do we have such good expanders in practice? Well, unfortunately, we have explicit constructions in the literature, but they're not efficient to use in practice. In particular, that construction requires a brute force search for a constant size graph with very special properties. And basically, the constant to do it in practice is like it grows exponential with this constant size graph. So it's beyond the reach of the.
But there's a simple randomized algorithm that gives you a standard with very high probability.
Yes, which is my next sentence.
But so what's the like? I mean, it's not really true. Like like, this is kind of ridiculous, right?
In what sense?
In the sense that I mean, explicitly. I mean, constructing one of these graphs with high probability is like I don't understand the full event.
Yeah, then you can sample a random graph, and the probability of not being a good expander is 1 over polynomial.
1 over calling in.
Yes,
1 over calling in what?
in the size of the graph,
Which can be.
and is not good for cryptographic
why
applications.
Some are random graph, because they're probably really so small.
For cryptographic applications, we want it to be negligible.
But concretely, it is. Concretely, the probability of failure, like in the GLS 2021 figure, the probability of failure is 2 to the -100.
Wait, why do you think inevitably you just need if A is expand the graph? Once you find one, you can use that. It's a universal graph for any scheme. Right?
Yes, that is true, but if you just sample random.
That is the security failure of it.
Why? But then if the graph is not a good expander, then the scheme won't be
Oh, but
secure.
I guess you can check that it's a good expander.
No, you cannot. It's actually hard to do it.
But the concrete probability of failure. I mean, like, forget the asymptotic statement.
Mhm.
Concrete probability of failure is already cryptographically good.
I don't understand what does it mean for a concretely cryptographic security. You just said that.
100 probability of failure is good enough for when conducted in public.
But only when n is kind of big, and also I don't fully agree with the arguments for concrete applications, sure. But
So
for
you're saying it's not efficient to check that if the graph is an expander.
no, we don't have it. So you need to check that all subsets of graphs expands, which is grows exponential.
I see. So the problem is like this failure probability is too high.
Or if you're still not happy, let me put it this way. So I'm interested in making this probability exponentially small. But if you're happy with any concrete probability like this, then your paper is more enough to use in practice.
But the thing is, if it's not an expander, does that affect the soundness of the zero knowledge?
Yes, if I can find a graph that does expand, that will lead to a code with small weight, with small distance, and then I can create a witness that is not does not satisfy soundness of the scheme.
Do you need to generate a different expander graph for like each application or something?
No, for the same size of the argument, you should suffice it to use one.
Oh, but even if you only need to use one, you cannot just generate one beforehand because you cannot verify it's an expander.
Well, I guess just with our algorithms, you can generate one with negligible failure probability, and that's to my view, that is good.
So your point is like asymptotically, you only need a constant size building block. So in theory, the running time is constant, but in practice, it's too high. That's the problem. You said you only need a constant size subgraph to build up to a bigger graph, right?
What do you mean?
No, explicit construction, you said not efficient. You need to search for a constant size.
Yeah, so that explicit construction is out of the question. That is true. The zigzag construction.
Yeah, you want a deterministic construction.
Yeah, deterministic construction, no one has ever implemented. It's not beyond reach of anything.
Oh, so that one is not the random line. The second line is not for the random.
The random line just shows random bipartite graph, and then through some analysis in Rial's paper, you can show that the concrete probability is 1 over n square, I believe.
I see. So you don't want to use this.
Yeah, I don't want to use it
Want to
for
use
cryptography.
that E that builds up from a
Yes.
small graph.
Yes.
Okay, I see.
Great. So yeah, finally that leads to our contribution in this paper, and also to clarify again, this is like the contribution from our paper.
There's a question in chat.
Does n grow with the security parameter, the size of the circuit, or both?
I mean, usually we think the security parameter should be asymptotically larger than log n. Yeah. So then, and can be like, for specific application, and over to the power square parameter is negligible.
Yeah, I guess the question is about if you want to verify a circuit of size n, what is the size of the expander graph you need to use? Like maybe that's the question. Or let's say your scheme has security parameter lambda and a circuit size of n, and now what would be the size of the expander graph you need to use as a function of lambda and n?
As a function of, so well, the expander graph is basically square root size. Yeah, the size of the expander graph is square root of n.
Square root of the circuit size.
Yes.
I see.
Did it resolve the question?
Who is asking the question online? George. Okay.
So how do I? Okay. Yeah. So finally, let's talk about our contribution in this paper. Is we proposed another approach to test whether graph is a good expander or not with overwhelming probability using this classical algorithm called maximum density of a graph. So how does that work? The density of a graph is very simple, just the number of edges divided by the number of nodes. And the maximum density just means that you compute the density of all subgraphs and take the maximum in the graph. And we already have a good classical algorithms to compute it in a reasonable complexity. So then the connection is as follows. So we observe that this is the example of subgraph I showed you in the previous slide. So fixing like two nodes on the left-hand side, because the degree of each node is a constant, then we always have 6 edges in this subgraph. And the more it expands, the more nodes you will have on the right-hand side, which means that the density of this subgraph tends to be smaller. On the other hand, if the expansion is poor, for example, the two nodes connect to only one node, then still the number of edges is fixed and we have less nodes in the subgraph and density tends to be large. So this gives a way to differentiate good expanders from poor expanders, like using this maximum density algorithm. In particular, if you look at the entire bipartite graph, and I run this maximum density algorithm on the entire graph, if all the subgraphs expands well, then the density of every subgraph tends to be small, and the total maximum density is smaller. On the other hand, if there exists a subgraph that does not expand, then the density of that graph will be larger, and that will be detected by this maximum density algorithm. So in this way, you can have a testing algorithm test whether the expander graph is good or not. And by applying this through like a rejection sampling, you just keep sampling the graphs until you satisfy this test, you're able to figure out a way to sample this expander graph with overwhelming successful probability. Like the failure probability is 1 over exponential in the security parameter. So, and that is the main contribution in this paper. And again, the real testing algorithm, because of certain conditions, is actually again randomized testing. So it's more complicated than this, but I'm going to skip the details here. Yeah. Okay, so then with that, then this gives a way to construct this expander graph that leads to a good expander code that can be encoded in linear time. So then using it to construct this polynomial commitment in this mechanism, as I mentioned, then you can actually achieve a linear time polynomial commitment that's also concretely efficient. And in our paper, we also have another approach to reduce the proof size to log d square instead of square root d. And we can also achieve zero knowledge with some random masking, but I guess I'm not going to talk about these in details here. So yeah, and then basically that's, I guess I'll just skip this part, and that's the part for my, this Orion paper, the linear time zero knowledge proof. And again, the key idea is this new algorithm to test whether expander code is good or not via the maximum density. And you can construct it by combining it with, for example, the interactive proof system, which also has a linear prover time. And that will give you a linear prover time zero-knowledge proof system. And also there's no trusted setup in the system. And to show you some numbers, I'm actually comparing it with, so this table compares it with some systems built from other techniques. And as you can see here, the prover time is kind of the best, both asymptotic and concretely using schemes constructed in this way. But and also the verifier time can be made pretty fast. But unfortunately, the proof size is actually quite big. And in general, this is true for all schemes based on this error correcting code. But we actually have some ongoing work to further improve this proof size using some other types of error correcting code.
So when you see the prover time is C, are you treating a bilinear group which one you don't use bilinear?
No, I don't use that. Yeah.
This is just,
So I'm talking about number of additions and modifications in the field. So this is a strictly linear
so
time.
what do you consider as unit cost? Is there like an operation on a RAM model with log and word size?
Well, I consider each operation in the field as a constant time operation. Yeah. So
But
kind
it's
of
not
yes.
expected, right? You're not counting how many
No, I'm counting additions and modifications in the finite.
addition and multiplication of log and size
Yes.
words.
Yes.
And
You also have to assume that hashing is a linear time.
Yes, hashing is, we also need to assume that hashing is a linear time. And that's true concretely because you have the CPU instruction to do it. And there also, in theory, exist these hashing in linear time, but they're not as efficient as these like SHA-256 in practice. Thank you. Do we have time to quickly go through the other one, or do you want
Yeah.
to start here?
I think you can.
Okay, yeah. So yeah, then
Another question in the chat. In the paper, you are using Virgo, so you require curve-friendly fields compared to other works. Is it essential?
Using curve, actually Virgo does not use an elliptic curve. It's also based on hashing and I think the IOP interactive arc proof and low degree test. So it does have to be FFT friendly because of the use of Virgo, but you don't have to be curve friendly using any particular elliptic curve.
I also have another, but what's the relationship between, Riyad is mentioning his paper, what's the relationship between these two papers? I'm still confused.
So this paper also builds on a sequence of prior papers on linear time prover zero knowledge proof. And then the Rails paper proposed this approach using the polynomial commitment combined with the sum check protocol to get a zero knowledge proof. So that's part I was talking about.
So his paper, you're saying his paper is also linear time, but it.
Yes,
like
so all these papers are using this expander code. Yeah, so that's why
No. Which papers are you using in standard code?
the Jonathan Budo's first paper and well, they don't have any implementations, but they all cite
Yeah.
DI.
Not the ones that you actually cited, yeah?
No,
Fielding paper is not a CK group paper. So
no,
PCG,
I'm saying yes, the T. So which one? PCG.
PCG 21 or 19 or something, right?
But so Jonathan Budo's Asia Crypt, and then there's a tensor code paper by Alessandra, Jonathan Budo, and Suchi, I guess, and then another recent paper to make a polylogarithm using the composition with PCPP. Yeah. And then also like Rails paper kind of the contribution, well, I see the contribution as making use of this tensor product to construct polynomial commitment and combine it together with the sum check protocol and construct a zero knowledge proof scheme.
Also showing that you don't need an efficiently decodable code. Prior works did not show this. But you can extract without an efficiently decodable code,
Yes.
which lets you to design a more efficient linear code, which we also did.
Yes,
So the
yes,
delta between that and this is, on top of that, you added the verification procedure for checking that the public matrix is
Yes.
correct.
yes. And also the proof composition to make it log square. Yeah. So yeah, again, it's to clarify it again, just like I always view that contribution is for all these constructions. Basically, if you want a code with provable distance, a constant distance, that the expander code is one of the few existing examples. Yeah, so all the papers are citing this Spielman code and DI 14 as the construction. But but we are trying to make it cryptographic, secure, and also concrete efficient using this new testing algorithm.
Is your testing algorithm, does it give a correct answer with probability 1, or I guess I didn't.
Correct answer, yes, probably if it did.
I see, so now
correct.
you can be sure with 100%.
No, it's the other way around. The correctness one, but the soundness is negligible. Yeah.
So if I give you a expanded graph, you will always output 1, but if
Yes.
I give you a non-expanded, you may output
Yeah.
some small probability.
Yeah, with negligible probability. Yeah.
So sorry, where does this data probability come from in your expanded testing algorithm?
So the one I was describing is just like a simple version of this. So I guess the gap is the example I gave here. It can't be true for all subgraphs because the size of this graph is like the size of the right set is on the order of the size of the left set. So if you count the subgraph of all the nodes on the left, it can't be expanding to, you don't have enough nodes on the right hand side. So the definition of a good expander, they call it loss expander. You have some constraints on the size of these subgraphs. Yeah. And because of that, if you run this expander testing on all the graphs, it always fail because the large subgraph does not expand. It can't be expanding because you don't have enough nodes on the right hand side. So it only expands if you satisfy these constraints on the size of these subgraphs. So in order to get around it, we need to do some random sampling. Yeah.
So basically your expanded testing algorithm itself is deterministic, but the randomness is coming from the sampling algorithm.
Yes, I need to sample some fairly reasonably subgraph here and then do the maximum density testing, and then sample another one and do it again. And I can increase the probability to negligible.
So you are not doing the maximum density on the whole graph.
No. So that will fail because of the reason details I explained. They will output, here's a subgraph that has a very large density, that is the graph of the entire left set. Because you don't have enough nodes to expand on the right hand side. So I didn't mention this detail, but that's a very good question.
So like how many tests do you need to perform? So like on the order of the size of graph, or
I think it's I think it's to the power of log n. I think something like that. So the total running time is still linear in the size of the circuit, which means it's quadratic in the size of the graph. I think that is the binary.
But I think the finding of the expanded graph doesn't need to be factored into account because you only need to, for every certain size, you only need
Yes,
to run
and
one.
there's also nothing related to the cryptographic operations. You just do it once in the pre-processing time for one particular application on zero knowledge. So I guess I'll just very quickly mention the other line of work. So here I already introduced that there are some cool applications of zero knowledge in machine learning. And in particular, I guess something that's not very familiar for this group is this fairness notion of machine learning models. So in the news, you can see that some of the existing algorithms of machine learning deployed in these applications are biased towards attributes like race and gender. Like, for example, the one used by the criminal justice to predict the recommitment of crimes, they're actually biased towards against black people. So these are not desirable in practice. And so in this notion, we usually call these attributes as sensitive attributes, such as gender and race. And it's actually usually not enough to just avoid them from the training set. You may think that I just exclude it from the set and I'm good. But actually, usually the bias is introduced through these correlated attributes implicitly. For example, you have an attribute of neighborhood or your zip code. That's actually correlated to the race of the community. And if you use this in the training set, your machine learning model may still be biased against these attributes. So in order to make it fair, this is a very active research, but some notions we've seen in the literature. For example, we have a statistical parity, meaning that we want the outcome of the machine learning model, probability that output 1, should be the same for the sensitive attribute being 0 and sensitive attribute being 1 for two different groups with different sensitive attributes. So in this way, you have the same positive rate, approval rate, regardless of your sensitive attributes. And another example is this equal opportunity, meaning that you take account of the ground truth. It's like for people from different sensitive subgroups, if they're qualified, if the y is equal to 1, then the probability of the machine learning model really opting 1 should be the same. So this is more like the accuracy on different groups should be the same. Okay? And they also have other notions of group fairness and individual fairness, but I'll just leave these two examples. So then using zero knowledge proof, we can actually prove such properties of machine learning models without revealing the machine learning model itself. So in this case, the witness is the machine learning model of the owner, and the owner commits to this machine learning model to the verifier, and then the verifier can pick a public data set with these subgroups of different sensitive attributes. Then the prover can actually prove that this machine model achieves the same accuracy on these two groups, satisfying the equal opportunity definition, or the same positive rate satisfying the statistical opportunity.
What is the public database for here?
Well,
You said there's a public database, but there's also a private database.
but the private model, the model is private, but the database data set is public. Yeah. So in this way, the prover can convince the verifier that actually my model satisfies, at least that's a good starting point, satisfies certain notion of fairness based on this data set. Yeah.
I guess the first notion is easier. For the second notion, you need to know some ground truth that's
Yes, but maybe for a testing data set ordered with labels.
Assuming the data set already has.
Yeah. Yes. So again, just so very quickly go over the kind of maybe the contribution part. So because of this motivation, we study this convolutional neural network, zero knowledge proof for convolutional neural networks. And the main message here is that, of course, you can just use a general purpose zero knowledge scheme to implement an inference, but the efficiency and scalability is not there yet. So in our paper, we propose a new protocol for proving convolution. So this is an example of convolution where you have an image in kernel, you just slide the image, the kernel through image, take the multiplication and sum them up as one element of the output. And the running time is order of capital N times capital K, where N is the size of the image, K is the size of the kernel. But we were able to design a new interactive proof protocol to prove the correctness of this computation in order of N time. So this is actually faster than computing results. It means that given the result of computation, the additional time to generate such a proof is even faster than computing it. Yeah. So again, I guess the main techniques, again, using this Fourier matrix, because this matrix is well structured and only has n distinct values in this matrix. So relying on this fact, we are able to design this scheme. Yeah. So finally, I just want to mention the last slide. Yeah, so actually, interestingly, this zero knowledge proof work on machine learning also motivates some research on machine learning fairness on its own. And I'm actually collaborating with my friend on this topic. So the approach I proposed is kind of relying on this particular data set, where you commit the model first and you prove that you achieve the same accuracy on this particular data set. But is that still fair on other data sets? Or who get to choose this data set? And do you choose it before the commitment or after commitment? All these questions are actually not addressed by the simple approach. So instead, in this ongoing work, we're trying to figure out some criteria, some equations, constraints of fairness of a particular machine model based on some distributional information about attributes instead of a particular data set. For example, you can take the distribution of, for example, the household income from these data sets released by the Census Bureau of the entire country or the entire region. Okay? Then given this distribution data, in order to satisfy this fairness notion like statistical parity or equal opportunity, we are able to derive some closed form equations on the machine model themselves for logistic regression and also some kernel-based methods. Okay? So then that means in order to prove that they satisfy the fairness, I don't need any particular data set. So I just assume that your input attributes will follow this distribution, and I prove that your model satisfies these equations I derived for the fairness of the machine learning model. And if that is true, I can prove that the machine learning model is fair for any data set that follows this distribution. And in particular, it is fair for all population around the country. So that is some ongoing work I'm working. So Yeah, and finally, I want to thank all my collaborators and students for their great contributions to these papers. And here's just a quick summary of my talk. Thank you for listening.
Besides proving the machine learning models are fair, is there any ways to train the machine learning model that can? So if you train it this way, then it can just prove to be fair or something like that.
I think that's a good question. I think there's a lot of ongoing research on that topic. So from my limited understanding about machine learning fairness, so a lot of papers pointed out that this phenomena exists, this bias exists. Right. And then many papers are doing this testing, figuring out for this data set, seems like there's some bias in this machine learning model. But how can you formally prove that a machine learning model is fair, and how do you even embed it into the training, regularizer of the training equation? So there are some papers on these things, but I've not seen kind of a unified framework for in order to achieve the fairness during training.
Are there any questions online?
Yeah. So I guess.
You're seeing why? I guess there was some question, right?
Oh yeah, so I saw some questions in the chat. So George was asking, do you see any viability to go beyond to the 224 circuit size barrier for larger? First of all, this 2 to 24, I think I said 2 to 25, but in general, a safe guess is seems like all of existing zero-knowledge schemes can't go beyond 1 billion gates. It's like 2 to 30 is basically the limit I know of. And in order to get beyond that, I believe we need to design some protocols with good memory efficiency, sublinear space size. And there's a recent paper called Gemini is doing this sublinear space, log-in space to do this thing. So the limitation is on the memory side. So we run out of memory if you want to generate proof for larger circuits than that. Yeah. So, and there are some active research to further improve that.
So you implemented your scheme, right?
Yes.
Linear. How does the concrete performance compare to other schemes?
You mean the ZKCN or the general purpose?
No, the first part of it.
The first part, yeah. So yeah, so it's about 3 seconds for a circuit with 1 billion gates, 1 million gates. So that's about 3 microseconds per gate. So for all succinct proof systems, I think this approach is one of the best in terms of power, and actually kind of matches the performance of a Ria's paper. Yeah.
But is your prover algorithm the same as this previous line of work, or your prover algorithm is also, because it sounds like you focused on this part.
Yeah, so for that polynomial commune part is the same, and then we have additional kind of proof composition algorithm to make the proof smaller.
Is the efficiency gain coming from the size reduction in the expander graph, or?
No, that is one time during the setup time.
No, yeah, but in comparison with the line of work that Ria mentioned,
yeah.
The previous papers, as I understand it, they're also linear prover time.
Yes.
So is the reason why you are faster is because you can find a expander graph that's smaller in size, or is it because your proving algorithm is different from the previous?
The proving algorithm is more or less the same, yeah. And the expander graph does help a little bit. We can be a little more aggressive in choosing the parameters of the expander graph because of this testing. But that only introduces a small factor in the random time. Yeah.
Thank you.
So does so if I understand correctly, so previous work used fast Fourier transform to do something like what your expander graph does.
Yes.
But add a logarithm factor to the side.
Yes, that's right. Yes. Yeah, and that is indeed the bottleneck of these systems. This FFT is actually one of the bottlenecks of these zero-knowledge proof systems. And then there's another question in chat. So this is a barrier that's essential imposed memory constraint for large.
It's the same, yeah.
Oh, okay, yeah.
Okay, thanks.
Is the interactive group in CKCN, is it GKR-ish or is it the Spartan-ish? It's a layered circuit, or
yeah, it's a layered circuit because the neural network is actually very friendly to this.
So for layered circuits, there's an additional memory saving that is sort of like folklorish. So you can get sort of square root D memory. Say that
Yeah,
you
kind of,
more in
yes.
Evaluation.
Yes, layer, you do it layer by layer.
And what's the depth here?
Depth is quite a lot because I'm doing this VG16, so at least you have 16 layers from name. But that's actually talking about 16 convolutional layers. You have activations, pooling, a lot of things. So
Oh,
you're
like
talking
1,000
about
layers.
hundreds of layers.
Yeah, so you get square root D, right? So the trick essentially is you evaluate the circuit forward and you prove it backwards, right?
Yes.
So if you threw away all the evaluations of the circuit, then life would be bad because you have to reevaluate the circuit every time. So it doesn't work. Instead, what you have to do is you keep sort of checkpoint layers in the circuit. And then you only recompute from the checkpoint forward each time you run out of stuff you've already used cache.
Okay.
So the optimal choice of checkpoint distance is square root of the depth. And if you keep sort of square root depth checkpoints along the way, plus the last sort of square root number of the layers, then what you're storing is 2 times square root depth in total. And you would sort of run the proof. And then once you've run out of stored stuff, you go back to your prior checkpoint, solve forward again, run the proof, go back to your solve checkpoint, solve forward, run the proof.
Yeah.
Right. So this way you go from order C to order C over, order like 2C over square root D or something like that.
Yeah, something like that.
So
Yeah.
you should be able to, for a deep circuit like this, you should be able to get pretty significant.
Yeah, that's a good point. Yeah, thank
Is
you.
this like a formal method? Or just a folklore? Checkpoint.
It's a folklore thing. I mean, I think the only place that it's been described is in some code on GitHub. As far as I know.
Yeah, all right, and thank you everyone.